The half-life of a first-order reaction does not depend on the initial reactant rate concentration. You can see that T1/2 is only equal to natural log of 2 divided by K. It is constant. It is the time for the reaction concentration to drop to half of its original value, and it can be calculated from the reaction rate constant, as you can see right here, meaning that E, all of the above are correct. Number 9, the half-life of a second-order reaction, so over here, the second order right here, does depend on the initial concentration. You can see that initial concentration is in there, and it is constant. It's the time for the reaction to drop to 1/3. No, it's 1/2, and it can be calculated from the reaction rate constant only, though that's not true. You need the original concentration, so A and B. Number 10, for a second order reaction, a plot of blank versus Blake is linear. For a second order reaction, it's 1 over concentration versus time. So 1 over concentration versus time on the graph right there, which would be C. And then for a first order reaction, a plot of natural log of concentration versus time. So natural log of concentration is on the vertical axis and time is on the horizontal axis. For number 11.5, use the graphs to answer the question below. And you can see that the only graph that ends up giving you a straight line with the data is 1 over the concentration versus time. So you know that it's going to be second order right here. The same data plotted gives you a curve and gives you a curve. It says write the unit for the rate constant. So the rate constant, remember, is the slope of this line. And since the slope is change in y over change in x, the change in y would be 1 over molarity over time. And so if you put this over 1 and then multiplied by the inverse, you'd get 1 over molarity times time, which is 1 over molarity times seconds, because time right here is in seconds. Which is the order of the reaction? It is second order. And which graph would you need to have a straight line for the reaction to be first order? That would be natural log of concentration versus time. So that would be graph letter B right here, because you can see that natural log of concentration versus time needs to be straight to be a first order reaction. On this side, notice we have a natural log of concentration versus time straight line with a negative slope, and it says calculate the value of the rate constant. Well, they're really nice here. They give us the actual equation of the line right here in y equals mx plus b form. And so this is our slope right here, 0.005. And that would be in units of 1 over seconds, because this is unitless, and this is in seconds. So concentration, 1 would be on the top and seconds would be on the bottom. Now you could also find it by changing y over change in x, but then you'd have to pick a couple of points, find those, and then actually calculate. Number 12.5, at elevated temperatures, it goes to products. We have concentration versus time data are plotted, and this time on the graph you can see that it is the natural log of pressure versus time, and it says calculate the value of the rate constant, and so the rate constant once again would be change in y over change in x. And so if I picked a couple of points right here, for example, maybe 5 right here, and let's pick a second one like maybe 3.5 right here, so those 2 points right there, I would have the change in y to be from about 3.5 to about 5, and the change in x to be from 0 to 30,000 right here, so 30,000 on this side. And if I took those numbers, I'd get negative 1.5, and my change would be 0 minus 30,000, so negative 30,000 right here. So negative divided by a negative is a positive number, and I'd end up with k equaling 0.05. And then the units on that would be unitless on the top here, and then seconds on the bottom, so 1 over seconds. More in the next.